Hi, everyone. My name is Olivia Haley, and I'm a graduate student at Kansas State University in Olathe. So, I study the use of ultraviolet light to inactivate human pathogens in agricultural water. But first, let me provide you with some background information on my topic. So, fresh produce is vital to the human diet because it contains a wide variety of vitamins, minerals, and health promoting phytochemicals. However, fresh produce is also among the most commonly implicated food items in foodborne outbreaks. And many of these outbreaks were actually traced back to the use of contaminated agricultural water. You see, water sources like rivers, ponds, lakes, even wells can become contaminated if exposed to fecal material, typically through events such as agricultural runoff or direct wildlife defecation. And when these sources are then used for irrigation or other such purposes, pathogens can transfer from the water to our produce and make us sick when we consume them. Currently, the fresh produce industry relies on the use of chemicals to kill potential pathogens in agricultural water. But some of these chemicals can be bad for our environment or even our own health. So the industry is looking for an alternative. So that's where my project comes in. So there's a long history of using ultraviolet light to kill human pathogens in our drinking water, but this technology has rarely been applied to agricultural water because of the high concentration of dirt and debris and other such particles, which can shield bacteria from the UV light. And then there's also an unknown financial aspect, as many growers are largely unaware of the cost of UV technologies. So we performed a study with two main objectives to determine the antimicrobial efficacy and the cost effectiveness of two different commercial UV devices. So the first device was a larger unit, which contained four high-powered UV lamps and was capable of flow rates up to 130 gallons per minute. And the second device contained only one lamp, was smaller, and could only go up to 9 gallons per minute. So we first performed an in-lab study as a pilot study to validate and ensure that our systems would be effective in simulated agricultural water. So with this successful validation, we then took the systems to the field and compared their efficacy to inactivate E. coli in three types of water sources: an unfiltered creek, an unfiltered pond, and a sand filtered creek. We found that our high powered system, which contained four UV lamps, was capable of inactivating 99.9% of E. coli in almost any condition we tested it in, which is indicated by the dark blue areas of our heat map. However, the low power unit, the smaller unit, costs substantially less. So, from this data, we then use predictive analytics to build a decision tool where fresh produce growers could input their water characteristics and their starting E. coli concentration. And the algorithm would then calculate and show what is their predicted log E. coli concentration after treatment. So, with this algorithm and the information that we've gained in this project, we hope to reduce the amount of harmful chemicals that are flowing into our aquatic systems and then support the increasing economic contribution of the specialty crop industry. So, your fruit, your vegetable, your tree nut industry in Kansas. So, thank you so much for stopping by my poster or my virtual poster, and hope to see you someday. Bye bye.